What's up, everyone, and welcome to episode 4 of Drew Sorta Knows Science. I'm Drew, and thank you for listening. So, today we're going to talk about a little bit of quantum physics, we're going to talk about a little bit of biology, and then we're going to talk a little bit about modern physics, as you can see behind me. So, let's get into it. First thing, we'll talk about a little bit of quantum physics. This is an article called Wiring the Quantum Computer of the Future. A novel, simple build with existing technology. And this is from phys.org. So, what is it? Well, scientists from Japan and Sydney have collaborated and proposed a two-dimensional design that can be made using current integrated circuit technology, which solves problems with 3D designs. So, you might be asking, what is a quantum computer? Pretty much, it's a computer that uses quantum mechanical phenomena to perform computation. And we'll go a little bit deeper into quantum physics itself in the future. But essentially, it's a computer that is just a lot more powerful. It can take in a lot more information and compute a lot more information a lot faster. So far, building a large-scale quantum computer, has been very difficult due to the architecture. So, basic units of quantum computing are called quantum bits. And these are typically atoms, particles, ions, and subatomic particles that exist in multiple states, making it possible to process large amounts of data very fast. They say, theoretically, that the computers have to be arranged in two-dimensional arrays where each quantum bit is coupled with its neighbor and an external control line. But when you increase the number of quantum bits, it makes it a lot harder to reach the quantum bits that are located in the interior of the array. So then the solution that they find is trying to use a 3D design to kind of like make it operate smoothly, but they find that it creates a lot more complexities, and wires tend to intersect with each other, and they don't want that to happen. So, scientists from the Tokyo University of Science, the Riken Center for Emergent Matter Science in Tokyo, and I think episode 2, I talked about the Riken Center using lattice clocks to prove Einstein's theories and stuff. And also, the University of Technology in Sydney have proposed a unique architecture solution. So they would take a quantum bit square lattice, and they would stretch out each column in the two-dimensional plane, and then fold each successive column on top of the other, creating a dual one-dimensional array known as a bilinear array. And this put all quantum bits at the edge, which made the wiring system a lot more simple than they had previously found. So they tested this arrangement through numerical and experimental tests, and they found that it's possible to run this system using existing technology with no need for a three-dimensional design. So it's a solution to most problems with a 3D system, and their work has only started. They plan on continuing to advance and test their tech to work on creating the first proper quantum computer. And I think this is very interesting because there's so many other companies, large tech companies out there that are also trying to do this. Companies such as Google, IBM, most of the probably predominant or dominant companies that you can think of in the world of technology are working on trying to build quantum computers. But I think it's very cool that, these guys have taken a giant step in approaching creating the first one. And they say, quantum computers, like I said, can process a lot more data a lot faster. And they say that, at some point, a quantum computer is most likely to, be in the size of like a laptop like this. But they say that that's very, very far into the future. And right now, once they would actually be able to create one, it'd most likely just be used in the world of the sciences. But hopefully that day is soon to come. All right, so next thing we're going to talk about is a little bit of biology. This is an article from Scientific American called Effective Psychological Therapy May Slow Down Cellular Aging. So, various psychiatric disorders can influence physical health. Things like depression and anxiety, and they're also linked to a shorter life expectancy. Now, recent research suggests that this may also be related to accelerated aging, but new work finds that a form of psychological therapy can change that. A study led by psychologist Christopher Manson from the Karolinska Institute in Sweden, found that cognitive behavioral therapy, also known as CBT, reduced anxiety for patients, but for some also improved cellular aging markers. So, telomeres, which are DNA sequences that are at the end of chromosomes, indicate cellular age. The shorter the telomere, the older the cell is, and the cell gets older through cell division. Now, a lot of studies also link stress and anxiety to shorter telomeres. So scientists took one blood sample, waited 9 weeks, and then they took another from 46 people with social anxiety disorder. In the blood, they measured telomere length and levels of telomerase, which is an enzyme that tries to maintain telomeres. And in those 9 weeks between the two blood samples, they put those 46 patients through online CBT, cognitive behavioral therapy. And at the end of the day, they found an increase in GPX levels, which is an enzyme that counteracts cellular damage by oxidized molecules. And they found that telomerase rose among those whose anxiety levels also benefited from the treatment. There's also indications that people with the lowest telomerase had greater improvements, and according to Manson, a longer experience will show even greater measurements, and they'll have more data over a longer period of time, so it'll be a lot more accurate. But at the end of the day, it suggests that behavioral changes can affect cellular health, and it connects the worlds of psychology and biology in the world of in the world of psychiatry. So the last thing that I'm going to cover today is talking a little bit about modern physics. Now, in episode 2, I talked about classical mechanics, which is a part of classical physics, which also includes acoustics, optics, and electromagnetics, which are all things that I would like to cover in the future, take a deeper dive into them. And I don't want to jump around kind of topics too much. I think I would like to kind of go in order of the way that they were I guess you could say, introduced to the world. And classical mechanics was kind of the first thing really brought on by Newton. But to me, modern physics as a whole is just so fascinating. And, a lot of the stuff in classical physics is, if you happened to be or become a physics student, classical physics, a lot of that stuff is generally what is covered in your general physics classes. And it was actually this past fall that I took a modern physics class, and I absolutely loved it, just because I began learning about these more specific topics that I had heard about and I knew about, but I didn't know really much about them. Especially things like relativity. I got very excited when I got to learn about relativity. But anyway, so yeah, I'm just gonna list off some topics, and we'll take a deeper dive in the future. But I kind of just want to lay it out there for you. So modern physics is essentially branches of physics within the 20th century and beyond. So things discovered within the 20th century, and technically things that could be discovered today. And it's based off of the two biggest breakthroughs of the 20th century, that being relativity and quantum mechanics. So some topics include atomic theory and the atomic model, black body radiation, the photoelectric effect, quantum thermodynamics, radioactivity in general, quantum mechanics and quantum field theory, and kind of like I said, general and special relativity. So some major accomplishments of this time period, would be discovering the elementary charge by Robert Millikan in his oil drop experiment, the discovery of the nucleus and orbiting electrons by Ernest Rutherford in his gold foil experiment, discovering of energy quanta by Max Planck, who is also the originator of quantum theory, and, like I said, relativity by, of course, Albert Einstein. So in the future, we'll take a deeper dive into some of these topics. Like I said, I kind of just want to lay it out there for you. And if you found any of it, I know it's might be kind of hard to find it, I guess, interesting. A specific one of these topics interesting, because I'm not telling you anything about it really. But like I said, I plan to do that in the future. But also, just modern physics as a whole, if any of it sounded interesting, please look it up. Take a deeper dive into it yourself. Because I know for me, this is, I think, the most fascinating time in the world of physics. But then again, with everything I talked about today, if you found any of it interesting, please look it up. Take a deeper dive into it yourself. Maybe you can learn a little bit more about it. And, if you haven't done it yet, go back, listen to episode 1, 2, and 3. All the topics that I covered in those are still very relevant. But yeah, if you enjoyed it, tell a friend, maybe share it. But I think that wraps it up for episode 4. Thank you for listening, and we'll see you next week. Peace.